So welcome to week 9 live session of Quantum Chemistry of Atom and Molecules. I am Mark Prabhu Chaudhary. I am a PMRF at the Department of Chemistry, IIT Bombay. So I'll be taking this course as my teaching duty towards the PMRF deliverables. So so whatever we have done so far is that first of all, the objective of these courses is to solve weekly assignments. We are not really doing that. We are solving some other numerical problems from the books like Griffiths, Macquarie, Simons, and Atkins. And I am here to clear the doubts, if any, from the current ongoing or the previous lectures. So as no participant is really coming to the online discussion session, mostly you are watching this thing from the YouTube, I am guessing. So we are not really clearing much doubts, but we are solving mainly the numerical problems. As you know that these sessions are recorded and available in YouTube for your future reference. So, and these slides and notes will be available to you. So today our main goal is that till now we have discussed different exactly solvable systems like particle in a box, then harmonic oscillators. Those have been taught in the class, as well as currently I guess um, perturbation theory, the approximation methods, the perturbation theory, variational theorem, and I think Harty-Frog is currently going on or has been taught in the last week. So the thing is that Sir Professor Datta has approached this perturbation theory for non-degenerate and degenerate system in a quite different manner. So what we usually see in the books and in other notes. So I'll today my plan is to give you that means I'll try to solve or no, I'll try to solve some problems from the perturbation theory, the time independent perturbation theory for non-degenerate states, and first I will derive the correction terms and the correction term to the wavelengths. First we will do that in the, I think it will be done in the first half an hour, and then we'll solve some problem. So let me start with that. So firstly I'll derive the I'll talk something about the perturbation theory and then I will go ahead. Okay, so let me change the ink. Today I'll not use red. Okay, so time independent perturbation theory for non-degenerate systems. Okay, today we'll discuss this. So actually the derivation and all is a little different what Professor Datta is doing or has done. So we'll do it in a different manner. Eventually we'll come to the same result. Okay. So now, so we'll talk about the, suppose there is no perturbation. So that is your Hamiltonian then, right? So this is, there is no perturbation. Okay. So this is your Hamiltonian then. And then what was your wave function? Your wave function is something like nth state is something like that, and as there is no perturbation, so from the Schrodinger equation you know that it is going to give you some energy of the nth state unperturbed, and you will get your unperturbed wave function back, right? So this is when there is no perturbation. Now suppose your Hamiltonian which is perturbed. Perturb means very small perturbation, not much. So that is Let me move the eraser for a bit. So this is the overall Hamiltonian, will be your unperturbed Hamiltonian plus a perturbation which is very small, which will be actually given by, suppose I am giving a parameter lambda, and this is the Hamiltonian. This lambda is nothing but a constant, which is actually, lambda is very small than 1. Okay, and so this is your perturbed Hamiltonian, perturbed part, small perturbation. So as you can understand, I have given the space here, so it is actually your Hamiltonian will be dependent on lambda. Okay, now what will happen to your energy and wave function? So suppose your wave function, so this is your wave function, so it will also be dependent on lambda. It will be something like, so when there is no perturbation, then there is perturbation, some perturbation, and it will follow a power series of lambda, which is something like this, and it will go on. So after this lambda q will come, it will not will be bothered with those parts. So this is a power series in lambda. And what does it means? So this is your unperturbed wave function. So this is the overall, this part is your overall, this part is your first order correction. And this part is your second order correction. Okay, correction to the overall with this lambda, not the sine just 1 sine second order, not like that. The whole part with the lambda square, this is your second order correction, and this is your correction to the Hamiltonian. Okay, small perturbation. So this is the Hamiltonian. Okay, let me think someone wants to join the Google Meet. Something is going on. Okay, stay in the call. Okay, let us come back to the thing. Okay, now what about the energy? Okay, the color has changed. So we'll have something similar to the energy also, right? So that will be energy when there is no perturbation to the zeroth order. So this is actually known as zeroth, first, second, something like that. It's not square or to the power 1. We should not say like that. So we should write this is sine zeroth, this is sine 1th, or first, this is sine second, something like that. Not to the power 1, to the power 2, something like that. We should not say like that. So, and this is your lambda, similar in a power series. So this is, and this will follow same thing, lambda square. So say mistake. En second, and it will go on, right? So again, and this is the same, this is the first order correction, and this is the second order correction. Okay, now it will follow the perturbed. After the perturbation, also it will follow the Schrodinger equation. So what it will follow the Schrodinger equation. So I should write the modified Schrodinger equation is H, the total Hamiltonian which is being perturbed, acting on psi nth, which is a function of lambda. It is not, so it will write in some different manner. It will the function of lambda, and it will give me an energy which will be E in lambda, and I will get back my wave function back. If this is true, then we'll write the things again. So if this is true, then let me rewrite this equation in the next slide, which will be my H function of lambda is working on this to give me energy which is a function of lambda. Okay, now you can write in here, and I'm getting back my wave function. So now I will write what my total wave function is, total Hamiltonian is, which is when there is no perturbation, then there is the small perturbation. Okay, what I know about my total wave function is right now 0 plus lambda sin 1th, then lambda square, this is lambda square, but this is sin second, and it will go on, and here we have the energy again. We have something like En 0 plus lambda En 1th plus lambda square En second. It will go on, and we have our wave function back. We have to write it in that manner, right? First order correction, then the second order correction to the wave, and it will go on. What we are going to get from here, we are going to write it in terms of we'll write it in polynomial order of lambda. So what I meant by that first I will write something which will be in lambda, which will have lambda square in common, lambda to the power naught, okay, which means 1. Then I will write something which will have maybe lambda to the power 1 in common. Then I will write something which will have maybe lambda square in common, and it will go on in such a way that will give me the ultimate, it is going to give me 0. So what do we have it here? See, so lambda to the power 0, we will have something like h 0 multiplying by working on sine 0th. Negative sign why I am writing, because there is equals to and then this part is there, so I have to take en naught multiplying by sine naught. So there is no lambda term, right? That is why I can take lambda naught. Lambda to the 0 there. Is that understood? Then the next part would be I will take where the lambda is common. So lambda is common, wherever lambda is common, see there is one thing. See, if this thing, this total of these things 0 plus 0 is 0, 0 plus 0 is 0. So then it will be in lambda to the power 0th. Lambda to the power 0 will be common. See, if lambda to the power 1 is there, so we need to take the product, from the product we need to take the terms as such a way that lambda is going to common. So see, we will find one order. So when h naught is multiplied by lambda sine 1, you will going to get lambda right there. So we will write that term first, sine 1. See, the total of this 0 plus 1, this is going to be 1. So we will have a pattern there. See, this lambda h1 is there and then lambda sine naught is there. So lambda will be common. So again, this h1 is there, sine 0 is there. So, and then the minus from this side, you will see that en0 is there, sine 1 is there. What do you else have? You have en1 and sine 1. Okay, this is what we have. No, this is wrong. See, both the a would not be equals to 0. So I will recheck. So lambda, when this is, so this part is done. We are talking about this en0 multiplied by sine 1. That is fine. Now we have lambda en1 sine 0. So it will be sine 0. Now I have to check for lambda square. Okay, I will need some more space. I'll maybe start from here. Okay, so let's see what we have in this side, the left hand side, as a lambda square term. As you can see that, and you can find a pattern, right? That 0 plus 1 is 1, 1 plus 0 is 0. So we need to take those terms where these are going to be whatever they are in the order term, that is going to be plus 2. Okay, I hope you understand what pattern I am trying to say. So if I take h naught, so I need to take something here from sine 2. What else do we have? If we have lambda h1, then we have to take this lambda sine 1. That then we have h1 working on sine 1. Okay. Do we have anything else? We don't have anything else, but we will have something in this part. So we will have en naught sine 2n, sine 2. What else do we have? We have minus en1 with sine 1. What do we have else? We have another term, that is en2 sine 0 and 0th. Now from here there is an, so we have this, so this equation we have in terms of lambda to the power 0, lambda to the power 1, and it will go on. Okay, so from here there is an understanding that if this coefficient, this lambda is never going to be 0. Okay, so So the coefficient in these cases are going to be 0, which are individual these terms. So see, so what we are going to get from here, I'll write in a different pen maybe. So this part, when there is no perturbation, so then we get, you will see it is true for that condition. We have already written this thing, right? That individually these all coefficients are going to be 0. So this is the first case. Okay. Um, it is not the first equation we get, but still let me write it. This is the first equation. Okay. Now see, from the lambda to the one term, so this is also going to be 0. So I'll write it in a maybe in this pen, that psi n1, then h1 psi n0th minus en naught psi n1 n1 psi naught, that is 0. So this is the second part. You can understand that this is going to help us in finding first order corrections. Why? See, in the equation we have psi n1 and en1, and the rest of the terms we know. So we have a chance that we can generate the first order correction. We can derive it to first order correction from here. What about the third term or the third equation? What do we have it from here? Write it in this color. The color is little different still. So we have another equation which is h0 psi 2 plus h1 sin 1 minus en 0th sin 2 minus en 1 sin 1 minus en 2 sin 0th. This is also going to be 0 because of the power series. So in these cases, all these coefficient terms are going to be 0 as the lambda is not 0. So, and from here you can see you have en2, and I hope will be that time we will be solving. We already have some expression for the first order correction to the energy and wavelength, so that we can use that or something like that to go to the. So this will be important to find second order correction. Okay. Okay. Now we know about the first thing. So I will love to start from the second part in the next slide then. Okay. Because I won't be able to finish anything in this. Uh, um, the so I won't be able to finish what I'm trying to do next. So let me start from the first this page. So sin 1 plus 1 sin 0. See, I am just following. I have not marked it up. I am just following what I said to you, that this order term is going to be 0. If this is this, then sin 1, and if this is 1, then this is going to be 0. I hope I have written it correctly. Now I'll look at my note. So let me look at my note, and I can see I have written it correctly, right? Hn naught sin 1, h1 sin 0 minus en naught sin 1 minus en1 sin 0. So you can actually write it in that way. Now what we'll do, we'll let us left multiply the equation with psi n zeroth, okay, star of that, a convex conjugate of that, and integrate all over the space. What does that mean? We'll get something, this is integral all over this space, this is the volume element, left multiply by psi n 0 star of that Hamiltonian, unperturbed Hamiltonian psi n 1, then we'll write it like that, psi n 0th complex conjugate of that. Now hn1 psi n 0 minus d tau. Now see, this en naught is actually, let me write it outside it. I'll write the en naught outside the integral because it is a constant now. D tau psi n star 0th psi n 1th then en1 d tau psi n star naught psi n 0, right? This is going to be 0. If I anything do with the right hand side, that doesn't really matter. So see, now we'll see that what we get. See, for this case, this is an if you check this part, psi n star not all over the space, and this psi n, these are already orthonormal, they are normalized psi n. So this part is normalized already, right? So we are going to get 1 from here, right? Okay, so we'll write in the next step then what we have. And one more thing, that this unperturbed, this part is, so this is, so our this operator is Hermitian, right? Is Hermitian. So what we can do with this operator, that suppose what we can write, let me show you here, that d tau psi n 0th star Hamiltonian and then psi n 1 is actually, you can write by the definition of a Hermitian operator, I can take an integral. I can put sine 1 here with a star. Okay, then I can write my, so this is just a definition of a Hermitian operator what we have already discussed and writing here. So, and this will become sine 0, and we need to take a complex conjugate of the whole integral. It's not the individual, the whole integral. And then we will see from this part, um, this operator cannot work on sine 1. Okay, this is not an eigenfunction of H naught operator, but sine 0 is an eigenfunction of this Hamiltonian, unperturbed Hamiltonian, right? So it will give me something En 0th, right? I hope you are understanding what I am trying to say. Sine 0th will give me back my sine 0th, and there is some complex conjugate sign is there, and here we will going to get, and complex conjugate of this energy term is always, that is always real, so we don't have any imaginary term, so it will be as it is, and the rest of the part is going to change. Like this part will be as it is, the sine 1 star, that is of star of that complex conjugate of that will going to give me sine 1, and it will give me sine 0 star. Okay, and you are going to see this is, I can write it in terms of this, in this order also, right? There is no operator in between, so I can write it like that also. If there is some operator, I could not have written like it, what I have done now, right? But it is just a interchange because there are no operators. So I will write here what I got: En naught d tau sine star 0 sine 1 plus d tau sine star 0, and we have sine 0, and see, we have the same term here as the first. Third and first are same, just a change in sign, so I guess we can cut it. And here, as we have already said, this part is normalized, so we are going to only have En1. So let me take it to the right hand side of the equals sign. So what do we have from here? We have, and what I said is, this first and third part are equals, so we'll cut them. So we are left with, so I'll take this thing on left hand side, and this we have d tau sine 0 star h1 sine 0. Okay, and this is in Dirac delta notation or bracket function. You can write it something like this: sine 0, your perturbation, and your ground, not the ground state but the 0th one. So this is for nth state. Okay, so okay, now this is your, so your first order correction is not this. Your first order correction is multiplied by lambda, right? So energy is going to be lambda En1, right? That is lambda into psi n naught hn, not hn, and lambda is small, very very small. So we have till now we have find out the first order correction to the energy term. Next, so next goal would be that we want to find out the first order correction to the wavelength. What is the wavelength? So to find the wavelength, we need to establish one thing that that the unperturbed states or wave functions make a complete set, means we can write any wave function with a proper linear combination of this unperturbed wave function. That is what mean by complete set, and the unperturbed wave functions are orthonormal to each other, means they are orthogonal as well as normalized, and that is how they are a complete set of a particular operator. And now we can write any wave function with a linear combinations of this unperturbed wave function. So we can write our first order correction, not really the first order correction, lambda is there, but sin 1 as a linear combination of the unperturbed wave functions, that is your sin 1 is Cm Im zeroth, okay, where m is from 0 to infinity. And as we are discussing of the nth correction to the nth state, so we should write a n here also. For the second, the coefficient may change, so we need to take care of these terms. Okay. Now we'll write the equation 2 again. So what was our equation 2? Equation 2 was h 0th psi nth 1, then h 1th psi n 0th minus en 0th psi n 1th minus en 1th psi n 0th. So now what we are going to do, that we are going to left multiply with a different with an unperturbed wave function, but a different one, not the same one as n. To get the energy, we have multiplied with psi n 0th star. Now we'll use a different unperturbed wave function. So if we left multiply the equation with psi L zeroth star. L is a different quantum number, right? Not the nth state but a different one. Lth and integrate all over the space, we will get d tau psi L star zeroth h zeroth psi n month plus integral d tau psi L zeroth star h1 psi n zeroth minus en 0 integral d tau psi L zeroth star psi n 1 minus en month d tau psi L zeroth star psi n zeroth, that is equals to 0. Now again we'll have to consider something here. First we can do one thing, that we'll put the we'll replace the expression for psi n1. Okay, let's do that. One thing we can do is that we can take both, as I have done it like this. Let us continue. Little psi L zeroth star. Now this is your m equals to 0 to infinity Cm n psi m zeroth plus d tau psi L zeroth star h1 psi n zeroth. What else? Here will come some d tau psi L zeroth star of that psi n1. Not psi n1, we need to write it in terms of psi m. That is again m equals to 0 to infinity Cm nth Im zeroth minus En 1th d tau psi L zeroth, taking a star of that psi n zeroth to 0. Now see, this is a very complex equation. This has become very complex equation. what we'll do here, we'll what can we do here? That actually become very complex equation. So now only for m equals to L. Okay, see, here is the summation. See, so should I, okay, I'll write another line, then I guess it will be more clearer. So let me take the summation side out of this thing. M equals to 0, infinity. Cm is outside the integral. Inside the integral there is d tau psi L 0th h 0th psi m naught. Okay, plus d tau psi L naught star h1. There is no change to this. Again I am taking my summation thing outside so that I can write these terms d tau psi L star 0th with psi m 0th minus n1. There is no change to this term. M 0th. So now I have to take some specific cases to solve this equation. One is that only for m equals to L, what will happen? Only for m equals to L you are going to see. So I can really write something here. Let me write this thing in a little bit different manner. This part Cmn. So when h naught will work on the psi m naught or the psi m 0th, it will give me, it is an eigenvalue equation, so we'll get back em 0th, and then inside the integral it would be d tau psi L star 0th and psi m 0th. Now see, for only for if m equals to L, only for m equals to L, this is going to be the normalization condition. For any other values of m, so m can be from 0 to infinity. Now when m equals to L, then only it will satisfy the normalization condition and it will get 1. In any other case, it will follow the orthogonality principle and you are going to get 0. What will happen here? In every other possibility, when m equals to same, when m equals to L, then only you are going to get a normalization condition, and for other values of m you are going to get is a orthogonal condition. What about this term? There is no dependency in L and m, right? So we have to put another thing that m not equals to n. Why? If L equals to n, so if m equals to n, then I need an condition, sorry, let me write it like that for once, that and L not equals to 1, not equals to n, it will be a normalization condition, right? Not the normalization. Achha, let me write it a little bit later. Let me put this condition a little later. Okay, let me write it for at least for this what we are going to get. So for this we are going to get CL, right? I have gone to the Lth state. Energy of this, and for this what we have now, we have psi L 0th star. I'm going step by step, I'm not jumping any step. Psi L 0th, right? So this is going to be a normalization condition. Then this is same d tau psi L 0th star h 1th psi nth 0. Now again in this side we are going to get only the Lth case, other things are going to be 0, that's why we don't really bother about that. Here it is nth, enth, and it is d tau psi L 0th star. M is L now, and it is en1 d tau psi L 0th psi nth 0th. So this, let me take it as it is negative, let me take it to the other side. So we have from here is that this is a normalized condition, this is a normalized condition. So in the next slide I am going to write, from here on I am going to take common the CL nth, this thing I am going to take common. So what I'll have is, what I'll have, I will take this thing into the, so for the next, achha, let me write it in the this fashion only. So what I will have, I will take this thing as common. So I got E Lth 0 this minus E nth 0, there is a minus sign. So this I have got for these things, and I have the second term I'll write d tau psi L 0th. So this is plus, right, plus d tau psi L 0th star of that first perturbation, and psi n 0th, I guess. Yes, the third term I have already taken inside the first, and here we have E n 1th integral d tau psi L 0th star psi n 0th star. Okay, we have this condition. Now what will happen if L is equals to n? What will happen if L is equals to n? So I will write it in a different fashion. When L is equals to n, what we will going to get? So CL become n. This term is going to vanish, right? En0 minus En0. Okay, so this is now n. D tau psi nth star psi n 0. Okay, so this is going to be 0. So see, we are going to get back, and this is one normalization condition. So we are going to get back our first order correction, or that part, not really the first lambda is left. We are going to get back this expression back, but that is not what we want, right? We want the correction to the wave function, and we don't, what don't we have? We don't know about the coefficient values. That is the variable here. So you need to find that. So these we have got earlier also. So we can't take L equals to N. So that's why I have written in a different pen. So let me go to different color actually. So now for L equals to L not equals to N condition, what we have? We have from here, we have CL to the power N EL 0th minus EN 0th. I'll rewrite the term, then you will understand why I am rewriting. Sin 0th. Now see, here the change is there. Okay. See, now when L is not equals to N, now this is not a normalized condition. So it will follow a orthogonal thing. So what we'll get? We are going to get 0 for that. 0 multiplied by N1 will be again 0. So we'll have, we'll be rewrite this expression, will be rewriting equals to minus d tau psi L star 0th H1 psi n 0th divided by E. So let me take care of this minus sign. Achha, I'll write it once. So I don't want to make any step jumps here. Next, I'll take care of this En 0 minus EL 0, and I'll write this thing in bracket function psi L, this psi 0th. Okay, it is something like that. So what is our wave function then, or the correction to the wave function will be, not the correction but, okay, I need to switch my okay. So psi n 1 is now summation of CL What was there? So in term of m, what we can say? So I'll erase this. If I have to write in terms of L, as I have told you that m equals to n, right? We are solving it for all values of m which are equals to L. Remember, right? At the far here we have used the condition only for m equals to L. For this condition, we are solving this. So, and one more thing, that L can't be 0. L can't, for we have applied another condition that L cannot be equals to n. So we can write it in this term also, right? Summation of psi m 0th h1 psi n 0th. So we need to appropriately use m0 there, right? And your psi n1 will be summation where m to 0 to infinity. Another condition will be add that m is not equals to n, as n is not equals to n. So that condition is added, and it is psi m 0th h1th psi nth 0th divided by en naught minus m naught into your psi m 0th. Okay. So your correction to the, or I should say first order correction to the wave function is, so then I will need, I'll have this lambda here, and I should add the lambda here also, and lambda is less than 1, that we know, but let me highlight this portion. Okay, now what we want to do, we want to find the second order correction to the energy. Okay, okay, so for that we will use our old pen, not this one, but it's the second order correction to the energy. So don't worry, we won't be solving or deriving this equation just 5 or 10 more minutes, then we have 5 or 6 numerical questions from this perturbation theory, and we have something from the assignment 7 also. We'll solve them together, and then we'll only finish the we'll close the date. Okay, so let us find the second order correction for the perturbation to the energy. So let us remember the, do you remember the third equation? Third means this one. So I'll go back to here, see this equation, that hn psi n hn psi n1. I know it would be tough to remember, but again I told you the trick that this 0 plus 2 1 plus 1, this should be there. Just let me check if I can write like that. Okay, so I know that we have, so I'll leave this place, only 2 from H and psi. You're getting my point, right? What I am doing here. I'm not saying you to mug up, but a clever way to write the things up. Equals to 0. So see, this would never be 0. So this can be 0 and 1. This only could be 2. Okay, it could be 1, it could be 1, then it is fine again. So what else? So it could be 0, it could be 2, it could be 1, it could be 1, it could be 2, it could be 0. See, you got all the points here. Now we'll rewrite it in a different manner. So we'll collect only in terms of, maybe you can say psi n second, then we'll collect in terms of psi n one, and as you can see, there is only one term in terms of psi n 0 to 0. What else do we have? Sin 2, what do we have here? We have h, oh, we forget to write the operator hats that I have kept. Now here we have en naught. Here what do we have in common? We have h1 minus en1 on it, and I have written all the terms. Now we will again left, here I am multiplying for the first time, right? Okay, someone there in the, no, I need to stay in the call. So I have to multiply the equation. The color has changed. Equation by, see, we'll go to our old friend sin nth 0 star and integrate all over this space to get, what will we get? We will get integral d tau sin 0th star en naught, we have sin 2 plus d tau minus en 1 in 1 minus d tau. So I have missed something here. So d tau psi n star 0th, psi n 0th star. I really hope that you guys are watching these videos from YouTube. Else it, we should not should, but if you watch, then I'll be happy that it is helping you in some other way. So here we have this equation with us right now. Now you know that this unpart of Hamiltonian from here, as it is an Hermitian, or you can say this whole thing is now Hermitian, right? So from this property itself, we can as so I'm not going to derive it, but 0 is Hermitian. So this is actually going to be 0. I hope you understand what I'm trying to say, because see, d tau sine star 0, what does it mean? 0 sine 2 will have d tau sine 2 from the definition of mathematical definition of Hermitian operator. We are doing this, right? I have done this earlier also once. Star, not the star would be there right now. Sine 0, right? And conjugate of all. From here we will get en0 outside, d tau sine 2 star of that, and I'll get back my sine 0 back, and it will be something en0 d tau, and I can interchange this thing again. As they are only wave function, there is no operator working. Just remember that if there is some operator working, then I could not have rearranged it like that. So again, it is going to be equals to this, right? This part, and it is going to be here. It is going to be 0, and so I can rewrite it that, um, and again this en2 I can take outside. So I can rewrite this thing this fashion. I should have en2 d tau sine 0th star. So now this is also a normalization condition, so we'll get 1 from that side. So I can take this thing in the left hand side. I can keep it like this, en2 and rest is 1, and this part I can write minus of, right? I can write minus of d tau sine 0th star, right? H cut, not H cut, H hat 1. So I'll write it in a different fashion. I'll now break it. I could have break it earlier also. So that is not the point. I could have done it earlier also. Minus minus plus d tau sine 0 star. I can write this outside en1th and sine 1. Now you can see that Okay, so here I will require one thing, that we know psi n1 is, we have write it in the previous note itself, right? That psi n1 is m equals to 0 not equals to n, and it will go to the infinity, and it will have what, cm nth and psi m 0th. So as it is not equals to n, m not equals to n, we get it, we got the condition later. Okay, it is not like that we have started from there, but we got the condition later. So what will happen then? Then we have en2, or not 2, en second minus, sorry, so let me write all the thing there itself, so it will be less happen that. So as I was writing, so I'll take the sum outside, which is m equals to 0 not equals to n to the to infinity cm nth, right? And then we have the integral, we have d tau, we have psi n 0th star, we have this thing, psi n, not psi m anymore, but psi m 0th, right? Now we can see uh, for the condition. So let me erase this condition here also. We know this. Okay. Now for a condition, now see here also we are going to get the same condition, that is now for m not equals to n, we are going to get minus so we do have cm. Okay, let me write. So m can go from 0 to infinity. Okay, so how should I write it? Okay, I have to take this summation thing, that m can be 0 and infinity. Now we are applying the condition m not equals to n, cm n d tau psi n star 0th star. This one term is fine, it hasn't changed, but see what will happen to the next term. I'll write minus minus plus summation, again m equals to 0 not equals to n to infinity. I'm just breaking that bracket, or I could have wrote that thing directly, but as I don't wanted to step, I wanted to show you the steps. This is a different part. D tau psi n I wanted to write the constant that is n outside, then d tau psi n zeroth and psi m zeroth. Now you see n not equals to m not equals to n does have a role to play here, and what will happen that it is going to be 0. So my whole this part is going to be 0, and I'm going to left with my en second is minus summation of m equals to 0 not equals to n. It will go, can go, m value can go to the infinity, cm nth d tau psi n star 0th star, this perturbation term, and psi m 0th. And that's not all. I'll play with it again. That what I have got, I'll write it again. So I have got en second to be minus summation of m to 0 not equals to n infinite cm n d tau psi n zeroth, the perturbation term, and psi m zeroth. We already have the value of cm nth, right? From here, don't we have this value cm n? So I'll write that here again in different color maybe, so one will be able to remember the steps, that whoever is watching from only the notes, they will be able to understand that from where I am taking this. What is this value? Cmn is en zeroth minus em zeroth, and at the top there is d tau psi m zeroth star psi n zeroth, right? See, so here I have written in the bracket formation, bracket notation. I can write it like that also. So that is nothing but psi m was at this position star. See, there is a similarity in, you can see a similarity there. Okay, so now again let me change my color to here. What I can write here is that 0 can't be infinity. I'll write this term as psi n h not h1 psi m 0, and here I have psi m 0th psi n 0th. So see, this is just a complex conjugate of this, so I can write the whole thing as I hope you got my point, right? So I can write this whole thing as mod square divided by, as the minus term is there, so what should I do? I can write it in not minus n naught. Am I making any mistake here? I may have made one mistake. Let me check. So in terms of here, let me rewrite this part a bit. Okay, I guess I can't change much. Hmm. Okay, may not have any mistake. So this is what we have right now. So this is your second order correction to the energy. Okay, so I had a doubt that your for a ground state for n equals to 0, uh, the energy should have always been the second order correction. So this is not the correction, so let me write down also the, so second order correction to the energy is actually lambda square En2, right? It is the case. It will be equals to lambda square m not equals to m0 not equals to n of infinity. Now psi m 0th h1th psi nth 0 square of that So I understand where I have made the mistake. I guess so. Yes, see. So erase the part. That's a good thing. That this part is here. You see, this is en2 and this is 1. Now, as this is Hermitian, we have this is 0 and this part is 1. Now I am taking this to the right hand side or to the left hand side, and this is plus, right? So this is plus, and here it is plus, so it will be minus and it will be plus. So that's the mistake I was talking about. I will come back to you why I was a little surprised with the answer. I thought I have made a mistake earlier also, but the earlier there is no mistake. The mistake was here in the sign, so it should be in plus. So I'll write it at least. So this is in plus, okay? So that there is no mistake, and now we have plus here, we have plus here. So this is the thing I was making a mistake. That is, this is n, this is m. So again this is your zeroth minus m zeroth. Okay. So we are not going towards the derivation of the second order correction to the wave function, as we want to solve a few numerical questions based on this. And one important thing, let me tell you that if n equals to 0, where is my cursor? If n equals to 0, then it is your ground state, right? Then your correction becomes lambda square is 0 to lambda square m equals to 0 not equals to n infinite your actually m not equals to 0. Now for this particular case, m not equals to 0, psi m 0th h 1 psi 0th modulus square, then E0 zeroth minus EM zeroth. So you can see that M will be M not equals to 0 means M is greater than 0, right? So 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 EM, so for this case EM, energy of the mth state, unperturbed state, is always greater than E ground state, the unperturbed energy of the ground state. So 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 this is this term, the correction to the second order is always negative, but for ground state this is also important. For ground state second order, I'll write it in a better format maybe. For G ground state correction and in energy is always negative. but for other n's, for other n where n is not equals to 0, or it is for other states, this statement is not true, always true. See, for n equals to 1, m could be 0, then it is positive, and for the other terms, means m equals to 2, 3, 4 onwards, it is negative. But there is one term, that is e1, e0, n equals to 1, there is another one time it can be negative. So for e equals to n equals to 2, you will see there will be two cases where the second order perturbation can be 0, negative. So only for the ground state, the second order correction to the energy is always negative, but for other state, the statement is not always true. You have to remember this question because these always come in CSI and NET. This statement kind of thing, or any concept from this can come. Okay, so this is one important aspect I wanted to discuss, and I wanted to show you this derivation, as this was not so this was somewhere or the other it was derived in Professor Datta's lecture, but I wanted to give you the another approach to how to we can write out this expression. Okay, so we don't have much time, but we will solve some question that is for at least the weekly assignment. These are from week 7 assignment. Let me write. So these are week 7 assignments, assignment solutions. Okay, I'm going to discuss whatever part I have already covered. So the turnover rule, so that you have already written, no. So that is hold for the operators only, those are Hermitians, right? For other it will not happen. Then again the expression for the first order correction to the energy from the perturbation theory is delta E. Then how much is that? So which will be the expression of the first order correction? We have shown you that both will be 0 and first order correction would be there, so there is C is only the correct option. Okay, now third, perturbation theory works for systems for which deviation from an exactly solvable Schrodinger equation is very small, right? 0, then it will be not perturbed. Undefined don't work. Large, we can't really use perturbation theory. Then perturbation theory only works for very small deviation from the exactly solvable equation. Okay, now question number 4, for a particle in a box with a x dependent potential as shown above, what will be the correction in the first order? Maybe what they wanted to know. See, I think sir has solved this question in the lecture. So here your Vx, actually V actually depends on, so it is following a linear nature, right? So it is actually dependent on your V is Vx, I say, dependent on um, x by, I should not write a here because from the image itself it is clear that your box length is a into v. Understand what I have written? V as a function of x, I could write this thing as x by a by v. Why? See, at x equals to 0, you can see your perturbation is 0. Now the perturbation changes linearly with x. So see, at when the perturbation at A, the perturbation is V given by V. So your perturbation V of Ax is actually x by A by V. So your uh, delta E is actually, so I'll write it here. It is, see, firstly, the wave function is, so I hope they want, so this is for the ground state, I guess. So ground state wave function is 2 by A sine A pi x by, sorry, not A pi x by A. Acha, one important thing I should also mention here, that see, here for ground state I have taken n equals to 0, right? And also we are saying that when m equals to 0, I was saying from here also that where m equals to 0 to infinity. See, now when you use your wave particle in a box theory, your m or n should start from 1, right? It will not start from 0. So it will vary from system to system. So like if harmonic oscillator is there, then m can be 0. If it is an particle in a box situation, then your m will start from 1. So you need to take care of that. I have derived it in a, for a general thing I have derived. Okay. Now your, it is going to be 2 by A sine square pi x by A, and your potential is x by A will also be there, x A by B dx, and it will go from 0 to A. So I will take the constant outsides, 2 b by A square, okay, 2b by A square, and 0 to A, x sine square pi x by A dx. Okay, so it will be, we have to use again the A by parts, right? Integration by parts, where we'll get um, x integration of sine square pi x by A dx. So I will take maybe 2 inside. So I will make v by square 0 to A x dx minus b by A square 0 to A x cos 2 pi x by A dx, right? So what I have done, the 2 sine square pi x by A is 1 minus cos 2 pi x by A. So that is what I have done. So I will do the integration for this part by parts, huh? So x cos pi x by A minus integration x, in the derivative of x is x 1, then cos pi by x derivative is sine pi x by A, and here to be A by pi, another integration would be there, and it is going from A to 0. So we'll get x by pi sine pi x by a minus a square pi square into cos pi x by a. The sign has changed a to 0. So when it is a, we'll get a square by pi sine pi, which is 0, minus a square pi square cos pi. Then also 0 for sine 0, and for this part we'll have plus a square pi square cos 0, which will come as 1. So this is we are going to get a square by pi square, because cos pi is minus 1, so it has become plus, and 2 a square pi square. So here we will have v by a square common. X will be x square by 2, which will in term will give us a square, right? X square by 2. Achha, x square by 2 a to 0, and here we have v by a square into 2a square by pi square. Okay. Achha, I have done one mistake. See, it is cos 2 pi x. So I would have got a by 2 pi here. So here it will be 4 a by 2 pi sine 2 pi x. Then this is also 2 pi x, ax by 2 pi, and here also it will become 2. So it will become sine 2 pi, which is 0. It would have been cos 2 pi, which is also 0. And then the other terms would be also 0. So actually we would have got 0 from here. You understand my point? We have 2 pi, 2 I missed. So we would have got 0 from here. So this is 0. So we have b by a square into a square by 2, which is b by 2. So this is the correct answer, D. Okay, I hope you understand the how I have done that. Now the next question is the expression for the nth order correction to the kth degenerate level of a system EKN. See, so that would be psi k 0. Now it is your perturbation, first order perturbation, right? Acha, nth order perturbation. So it would be there, and it would be psi kth, okay, n minus 1, and they are saying this is v in all 4 cases, so I'll also write it as v. So it would be psi k 0 v n minus 1. So B is the correct answer here. Okay. What about question number 7? So question number 7 says that a particle of mass m is confined in a finite potential well with a boundary conditions that is given. Okay. So first is same as particle in a box. So, and it is subject to a perturbing potential of Vpx is equal to P naught sine 2 pi x by L in the well. Let E1, E1th and E2nd be the first and second order perturbation to the ground state energy respectively. Which of the following is or are true? Firstly, I told you that second order energy correction to the ground state is always going to be negative. Which have this option? The first, I can say that my answer lies in either in A or B, A or D, because E2 is less than 1. Now I need to find out this integration only. So I have to do this integration. So I need one blank page. So sorry. Okay. So we have okay. So first order correction to the energy I can write. Should not say this is the first order correction, but that is what they wanted to see. That would be psi 0, right? Then it is Vpx, and again it will follow this, right? So now it is what 0 to L. See, V0 sine 2 pi x by L. V0 sine pi x by L. What else do we have? We have root 2 by L sine. So for ground state, so it is pi x by L. Here also it is 2 by L sine pi x by L dx. Now 0 to L, it is 2 by L P naught. These are the constant I took it outside. We have sine square pi x by L with sine 2 pi x by L also, and dx. Now we know to be 0 by L, 0 to L, I can take these two inside and I have 1 minus cos 2 pi x by L, right? Sine 2 pi x by L dx. So I'll do take cos 2 pi x by L as P. Okay, so it would make my life a little easier that 2 pi by L sine 2 pi x by L dx is equals to minus dp, because cos derivative is there. So, and what will be the change in my limits x to p? If x is already 0 to L, so if it is 0 to cos 0, my p will be 1, and when it is L, my cos 2 pi to that is 0. So it will change in something like this, that from 1 to 0, 1 minus p dp, but a negative sign is there. So b0 by L, 1 to 0, p minus 1 dp, which is nothing but V0 by L P square by 2 minus P 0 to 1 V0 by L 0 0 0, then it will give me minus 1 by 2 plus 1, that is V0 by 2L. So what do I have option? So did I made any mistake here? In one case it would be less than 0, and one case it should have been equals to 0. 0 to L. अच्छा, cos 2 pi. Cos 2 pi is 0 or 1? Cos 2 pi is actually 1. So that is the mistake I have done here. So see, cos 2 pi is always 1, right? Cos 0, so 2 pi means you will again come back to 0. So it is cos 2 pi plus 0. So it would be plus cos 0, and it is 1. So I should not have done this many calculation to see. This is a very irresponsible thing. I am very sorry. So 1 to 1 limit is always 0. So your E1 is 0. And you know, yeah, already that E0 second order is going to be negative, right? Negative means less than 0. Okay. So actually this is correct. Did I use these things somewhere else also? I guess this cos 2 pi I made 0 here. So did I make any mistake here? Let me check. Yes, I guess so. If I have used that particular formula there, then there should have been a mistake, right? Let me check. Yeah, so I told you this is cos 2 pi is 0, but that is not the case. See, from first term we are going to get 0, then we are going to get a square by pi square, because this cos 2 pi is 1, so that is 0, then it is 0 plus cos 0 is 1, so we are going to get this, so minus or plus, ultimately we are going to get 0. So that is what I have taken, but I may have said it incorrectly. Let me correct myself, and that is the thing. Okay, so we have one more question, and then I had a lot of question problems from the numericals, what we can solve the next day. But let me at least solve this question number 9 now. So at a particle of mass m is confined in a part, again the same, just you need to see the first order correction, which is going to be psi 0 0 to your beta x psi 0 0, so 0 to L 2 by L sine square pi x, the ground state it is mentioned already, and x dx, right? Beta x, I can take the beta outside, so let me write beta by L. Okay, integration 0 to L x into 1 minus cos 2 pi x by L dx, which is beta by L 0 to L x dx, and beta by L 0 to L x cos 2 pi x by L dx. So as I think I have shown you here, from here you have got the idea that what does integration 0 to a x cos function cos 2 pi x by a is yielding, that is yielding 0, right here. So this is nothing but your x cos 2 pi x by a dx, right? Integration here, right? 0 to a. So I have done that part only, so I'll not, so it is yielding you 0, so I'll not do this again, but you know this is going to give you 0, so it will be beta by L, right? Beta by L x square by 2 L to 0, which will again give you beta by L into L square by 2, and that is beta L by 2, right? So your answer is going to be the second one, beta L by 2. So with that, let me show you the questions what I have. I'll give you these questions with this note, so that we'll start from here. We'll solve these questions and then I guess we'll take, so these are some problems from JTL, and these two problems are from JTL, and this problem is from this is also from JTL, but an example problem you can find it there. And then we have a few problems from the Atkins, the perturbation problems. I hope to solve these problems in the next class, but you can always look at it. Okay, you can always look at it and try to solve it yourself, and then it would be good interaction if you come, if someone of you which is watching the class, if you can come during the next session, that is uh, 2nd of 2nd of October, which is actually a holiday, 2nd of October 2023. If you using the same joining link, if you can come to the site, if you please try to solve it yourself, the questions I'll give it. um, I've shown you, whoever is there in the online, you can take a picture or take a screenshot and try to solve. And obviously whoever enrolled in the NPTEL, they are going to get the slides and the notes, they can try solving themselves, and we'll have a good discussion, and also we'll try to solve some more problems from variation theorem or other approximation processes, what is methods what is already there. So with that, today I am going to end that meeting, and I hope you will be you have uh, been benefited at least from the derivation and on the assignment solvent solutions, and we'll try to solve some more. You can solve that, and we'll solve some more problems, numerical problems, in the next session onwards. So with that, I thank you for listening, and I'll stop the program here, and hope to meet some of you in the next meeting. Okay, bye bye.